For decades, our entire cosmological framework has hinged on a delicate, almost precarious balance of unseen forces and completely undetected particles. But what if we've just been looking at the wrong thing this whole time? What if the universe isn't actually mostly dark, but is instead operating under a profound geometry that we just haven't fully recognized yet? Welcome to The Explainer. Today, we're jumping straight into a radically different, paradigm-shifting framework, the Integrated Toroidal-Syntropic Model, or ITSM. It really all starts with one incredibly provocative question. Why are we inventing invisible dark matter and dark energy when pure geometry solves the entire puzzle? That right there challenges the absolute foundation of our standard cosmological paradigms. It directly confronts this growing crisis we're seeing in modern physics, essentially asking us to completely rethink the fundamental architecture of the cosmos. Okay, let's dive into this. The standard ΛCDM model essentially demands a universe that is 95% invisible and entirely undetected by any direct observation. I mean, think about that. We are asked to just believe in 27% dark matter and 68% dark energy. That leaves a measly 5% for the normal baryonic matter, the stuff we can actually see, touch, and interact with. We're just accepting that the vast, overwhelming majority of reality is made up of these phantom substances, just to make our math work out. And the reality is, this 95% dark framework is totally cracking under the weights of modern, high-precision data. We're seeing some really severe, persistent discrepancies that are just breaking the paradigm. Take the Hubble tension. That's a massive 4.2 sigma discrepancy in how fast the universe is actually expanding. And then on a galactic scale, standard dark matter simulations completely misalign with actual telescope observations, giving us persistent issues like the Corpuscle problem and missing satellite galaxies. So to patch all these holes, current models over-rely on endless free parameters. Essentially, these are just invisible dials that scientists manually tune to force their equations to fit reality. To deal with this crisis, physics has kind of split into two failing extremes. On one hand, you have the standard paradigm leaning heavily on unseen, undiscovered particles. On the other, you have modified gravity theories, stuff like MOND or Tevez. Now, sure, they can fix galactic rotation curves without using dark matter, but they rely heavily on arbitrary curve fitting. And honestly, more importantly, as we saw with the multi-messenger observation of that famous 2017 neutron star merger, many of these alternative gravity models just fall apart under strict relativistic tests because they end up predicting gravitational waves traveling at the wrong speeds. Well, this brings us to a radical yet mathematically rigorous alternative, the Integrated Toroidal-Syntropic Model, or ITSM. Instead of forcing us to choose between invisible particles or totally arbitrary gravity modifications, ITSM completely replaces dark matter and dark energy with topological superfluid dynamics. The foundational axiom here is pretty wild. It argues that the vacuum of space isn't just an empty, passive void. It's actually a continuous, three-dimensional, pressurized medium called a superfluid plenum. So think of space less like an empty room and a lot more like a pressurized ocean. I want you to visualize this with me. Strip away the idea of those hypothetical, glowing dark matter halos surrounding galaxies. Just toss them out. Instead, imagine the fluid mechanics of a continuous, pressurized 3D vacuum. In this framework, galaxies aren't wrapped up in invisible particles. They're actively interacting with an incompressible fluid. So that flattening of galactic rotation curves that we normally just attribute to dark matter, it's perfectly explained here as localized directional fluid pressure and fluidic torsional drag. And here is where the model gets incredibly strict. The ISM requires absolutely zero free parameters. None. Everything is derived purely from three fundamental variables. You have baryonic mass, which is just the normal matter we can see, the Hubble Flow, our cosmic expansion rate, and toroidal geometry, representing the vacuum's topology with 2 pi. There are literally no invisible dials to tune. Everything has to mathematically lock into place based solely on these three constants. In physics, a model with zero free parameters is the ultimate tightrope walk. It either works perfectly or it completely fails. For instance, let's look at the famous MOND acceleration scale. That specific low acceleration threshold where galaxies just stop behaving according to classic Newtonian physics. In other models, this threshold is basically just an empirical guess. It's a number they plug into the math to make it match telescope data. But in ITSM, this exact number, 1.08 times 10 to the negative 10 meters per second squared, is mathematically derived from scratch. It is a direct result of macroscopic circulation quantization. It's calculated simply as the speed of light times the Hubble flow divided by 2 pi. It's pure geometry. No guessing required. Now, what's really interesting about this is how beautifully that pure geometry translates into actual real-world observations. Looking at the baryonic-Tully-Fisher relation using the Spark Galactic database, you can see this line running through the graph. This is definitely not just a line of best fit drawn through the data points after the fact to make things look nice. This is the zero free parameter geometric prediction derived natively from the ITSM framework. It perfectly maps the galactic rotation data using strictly fluidic physics, completely eliminating any need for dark matter halo. And the model isn't just loosely estimating this stuff either. When researchers used advanced statistical stress tests, specifically MCMC distribution modeling across 175 high-fidelity galaxies, they found that the ITSM achieves a globally locked fit. We're talking about over 3,000 distinct kinematic data points here, and the framework holds mathematically stable without inventing a single invisible parameter to fudge the numbers. Let's pull up a quick holographic scorecard and compare ITSM to other alternative fluid models because the structural differences become pretty stark. While superfluid dark matter relies on Bose-Einstein condensates and dipolar dark matter depends on gravitational polarization, the ITSM governs its dynamics simply using an acoustic stress tensor. And where those other models genuinely struggle with gravitational lensing, the ITSM accounts for it effortlessly. The directional vector shear of the fluid field physically bends the light directly. Simple as that. Okay, so let's move to the other massive cosmological mystery we have to tackle: dark energy. How does ITSM handle it? Well, it resolves it through something called the syntropic source vector. Instead of proposing some phantom energy pushing the universe apart, ITSM describes a thermodynamic contraction of the universal boundary. This creates syntropic volume decay. And the amazing thing is this naturally and organically mimics an evolving dark energy equation of state. It perfectly matches the highly anticipated 2024 DESI baryon acoustic oscillation data, and again, it does this without introducing any extra imaginary fields. And this brilliantly illustrates the sheer macro-scale capability of the model. Consider the cosmic microwave background. A lot of alternative gravity models completely fail right here, because they just can't explain the early universe's thermal footprint. But the ITSM fluid boundary mathematically predicts the exact acoustic peaks of the cosmic microwave background. It actually arrives within a fraction of a percent of the ultra-precise Planck 2018 baseline. Furthermore, the ITSM successfully preserves the critical baryon acoustic oscillation wiggles and the large-scale clustering structure of the universe, essentially the cosmic web as we know it. It scales naturally with the higher Hubble expansion rate, which provides the macroscopic stress needed to stabilize clustering dynamics. And it does all of this entirely without a single solitary particle of cold dark matter. So the crucial point we really need to highlight here is that this isn't just some elegant mathematical theory that sits on a chalkboard. It is a strictly falsifiable scientific framework. It actually puts its neck on the line with highly specific, testable predictions across multiple scales. It explicitly predicts a precise acoustic resonance in the upcoming nanograph pulsar data. It predicts the very existence of mature, rotating disk galaxies at extreme distances, which, by the way, the James Webb Space Telescope is finding right now. And it predicts that the famous bullet cluster separation is just a fluidic acoustic wake, not collisionless dark matter passing through itself. As we wrap up this explainer, I really want you to consider the sheer elegance of a purely geometric universe, especially when you compare it to one patched together with invisible matter and phantom forces. To quote the framework's core claim directly, no invisible halos, no phantom energy, just 3 fundamental variables. The scorecard is locked. If the cosmos truly operates on this breathtakingly simple geometry, it absolutely forces us to ask, what other fundamental truths about reality are we currently hiding in the dark?